Welcome to Quantum Curious, and in today's video, I'm going to discuss an important property of entanglement. And this property is called monogamy, and this characteristic is very useful in quantum cryptography. So, this is the outline of today's video. First, I will discuss what is monogamy, and then I will discuss how to quantify this characteristic of entanglement. And then we can understand this property using a non-local game with three players instead of two, as we discussed in the previous lecture. So let's start with the introduction. Consider we have two parties, A and B, and they shared maximally entangled qubits. So the whole system can be described by an EPR pair. So this state we have studied many times in the previous lectures, and we know that it is a maximally entangled state. So how about a third state? How about a third system? And can we have uh, a correlation between uh, EPR pairs and a third system C called Charlie? Can there be an EPR-like correlations? So according to Ullmann's theorem, if this state is pure as it is and it has only one non-zero eigenvalue, then the purification of this state can be written as this. And it is an arbitrary uh, basis, and there can be many kind of these bases that are unitarily correlated with each other. So let's see, is this state is entangled? Or in other words, the system C is entangled with system AB or not. We have to check this. So we can check this by taking trace of A or B, then see that either the system A is correlated with C or either system B is correlated or entangled with C. So for the first case, if we take the trace of B out of this state, then we get this state. And you could see that uh, not only the state C, uh, row C, is uncorrelated with the system A, uh, it is uh, it's also, we can see that system A is maximally mixed from the point of view of C, and it is completely random. So we can say that for the EPR pair that are maximally mixed or maximally entangled, there is no other system that can be correlated with this EPR pair. And this is the monogamy of the EPR pair. So if we have two systems that are correlated with each other and they are entangled, and the entangled is the kind of PR pair and they're maximal entangled, then uh, the monogamy property says that there is no other system that can be that much strongly correlated with the system that are correlated with EPR-like state. So this property called monogamy is very important in cryptography. So consider we have Alice and Bob and they share uh, EPR pair. Then Eve cannot have correlations uh, stronger than the EPR pair with either of the system. So this property can be very useful in cryptography, especially in quantum key distribution. So now we have discussed what is monogamy, and we have somehow saw the qualitative side of it. Now we want to quantify the monogamy. So previously we saw that if the two parties or the two systems are entangled and maximally entangled with each other, and they form an EPR pair, then there could be no third system that can be entangled or correlated with the system that are entangled or maximally entangled with each other. So what about the general case? So consider we have G at Z state, and it is a tripartite state, and we could see that there is a strong relation, strong entanglement between three systems. So there is a bipartition entanglement between these three subsystems. So we want to know that uh, they, that there is either there is a kind of coalitions or entanglement between either of the two subsystems if we drop out the third system. So first, we can check it by taking the trace of C using this state, and we can easily obtain this result, and this show that the reduced state is not at all entangled, rather it is an separable state. So if the three systems are entangled with each other, then the reduced system of two subsystems is not only uncorrelated, but it is also a separable system. So this kind of correlations is slightly stronger than classical correlations, but it is very weak for it is very weak than the entangled system. So entanglement between pairs is weaker than in a pure pair, and we want to quantify this strength of entanglement. So for the pure state, we have seen some entanglement measures called Schmidt rank or entanglement entropy before, but they only work for pure state. So there is generally no defined entanglement measures for the density matrices. So this is a very active area of research to find the entanglement measures of the density matrices. So for the tripartite system, uh, with system A entangled with system BC, there is an inequality that they have to or they should uh, follow, and this is called monogamy or entanglement. And we can uh, uh, quantify monogamy using this inequality and some related entanglement measures. So now we have saw that if two pairs are strongly or maximally entangled with each other, then there could be no third system that could have some kind of entanglement with the two systems that form the EPR pair. And we saw that if the three systems are entangled with each other, then if we drop out one system, then there is no correlation between two remaining systems. So in order to solidify our understanding, we can play or we can consider a three-player CHSH game. So it is a very intuitive way to look at the monogamy of entanglement via a non-local game. So consider we have Alice, Bob, and Charlie, and they will play CHSH game simultaneously, and they have to satisfy these relations. So consider there is a referee, and uh, the referee is going to give some questions like X to Alice, Y to Bob, Z to Charlie, and they are all random bits with same probability, and their answers would be A, B, C, respectively. So can they win? Can they always win this game using some entanglement? So you can guess that they could not, because we have seen that the monogamy of entanglement will not allow this kind of winning probability that will surpass the classical probability winning probability. So consider another variant of this game. So we have referee, and referee has the choice to select randomly two players from the three players, and the referee will tell these two selected players that they are selected, but they will not know that which two players or to whom he or she is going to play the game. So let's suppose that we have three players, Alice, Bob, and Charlie, and uh, referee picks Alice and Bob. So Alice does not know that to whom she is going to play the game. Either it could be Bob or it could be Charlie. So if she is going to consider a quantum strategy in which uh, she is going to distribute entangled pairs, CPR pairs between her and between other players, then it is not going to work because she does not know on which pair she has to make measurement. So now let's consider she is going to play the game and she will consider the GHC game, that is the tripartite entangled state. But we saw from the earlier slide that that could not be the case because in the GHC game, the reduced state does not have that kind of entanglement. So in this case, the quantum strategy will be equal or less than the classical winning probability. So the quantum strategy will reduce down to the classical case in that case because entanglement does not have that kind of advantage over classical strategies because of the monogamy of the entanglement. So this is for today. And so we discussed what is monogamy and how can we quantify this property of entanglement and how can we solidify our understanding through a three-player CHSH game. So thank you for today. If you like this video, kindly subscribe and click the bell icon and like this video. Thank you.